Okay, so now let's talk about the physical properties of some of our four, or all of, I guess, our four new functional groups here. Yeah, so we did talk about how alcohols are used as hand sanitizers. Phenols used to be more popular as those anesthetics, those topical antibiotics. Now they just use like straight ethanol because it does a great job of killing the bacteria on your hands. We're going to learn about how to classify alcohols, okay? So alcohols are classified as either primary, secondary, or tertiary. Let's see how to do that. So first of all, when you classify an alcohol, you're going to look, so here's my OH group. You're going to look at the carbon that that's bound to. And you're going to ask how many other carbons is this colored blue carbon bound to? If there's one, it's a primary alcohol. Again, find your OH group, find the carbon attached, and count how many other carbons that's bound to. In this case, 1, 2. So this would be a secondary alcohol. Okay, again, find your OH group, find the carbon it's attached to, and count how many carbons that's bound to. In this case, 1, 2, 3 other carbons. So that's a tertiary alcohol. Okay, so this is just a simple classification of alcohols that we can do where we look at the carbon that OH group is bound to. Notice that an OH group can only ever be bound to one carbon. It only has one bond available. So what we're doing is we're looking at that carbon that contains the OH group, and we're counting how many neighbors it has that are carbons. Okay, so let's classify these guys as primary, secondary, or tertiary. We're going to find our hydroxyl group, our OH group. This is the carbon that that's bound to. And that carbon is bound to 1, 2 other carbons. So this would be secondary. Okay, next problem, we're going to find our hydroxyl group, our OH group. Identify the carbon that OH group is bound to, and then start counting. In this case, it is only bound to 1 other carbon. So this is a primary alcohol. And then our last example, again, find the hydroxyl group, identify the carbon that it's bound to. This is bound to 1, 2, 3. So this would be a tertiary alcohol. The reason why we do this is because primary alcohols undergo different types of reactions than tertiary alcohols do. We'll see this when we discuss the reactions in the last lecture here. Okay, boiling point. So first of all, we talk about boiling point a lot when we talk about physical properties. There's one thing I want to point out as to why we talk about boiling point. Boiling point, if you think about what boiling point is. That's the point at which a compound goes from the liquid phase to the gas phase, right? In the liquid phase, everything is really close together, everything's touching one another. And in the gas phase, they're very separate, okay? So what you're doing when you're boiling a compound is you're breaking the interactions that neighbors have with one another. This is what we call intermolecular interactions. Okay, right, so intermolecular meaning between two molecules and their interactions. If two molecules are really strongly interacting with one another, it takes a lot of energy to separate them into the gas phase. So that means that they have a high boiling point. So high BP means strong intermolecular interactions. Low BP is weak intermolecular interactions, right? So boiling point we kind of use as a measure of how strongly molecules are interacting with their neighbors. Okay, we saw that hydrocarbons have relatively low boiling points, and they get lower and lower the smaller that those hydrocarbons get. So that means like methane is not interacting with its neighbor very strongly. When it comes to alcohols, they have substantially higher boiling points. That's because of something called hydrogen bonding, okay? Water, I mean, this might not be super apparent, but water, for as small of a molecule as it is, has a super high boiling point, okay? It's really teeny tiny of a molecule. We think it's even smaller in terms, well, I guess it's on par in terms of mass as ethane or as methane, and has a way higher boiling point. That's because water interacts very strongly with its neighbors, and it does so through something called hydrogen bonding, okay? When an oxygen is bound to a hydrogen, the oxygen takes on a partial negative charge, and the hydrogen takes on a partial positive charge, okay? So that means when these guys are in solution, you can have the neighboring hydrogen interacting very strongly with its neighbor's oxygen, right? The positive end of a hydrogen interacting really strongly with the negative end of an oxygen. Same thing over here. So we have our hydrogen interacting very strongly with that oxygen. And because alcohol groups have both oxygen and hydrogen, they have like what's called a donor and an acceptor for hydrogen bonds. So not only can they be accept hydrogen bonding from other hydrogens, they also have a hydrogen that can donate to a neighboring oxygen. Whoops. All right, so alcohol groups are able to form very strong intermolecular bonds with their neighbors. If we go to ethers, they have that oxygen, so they can accept these hydrogen bonds, right? So they have that negatively charged oxygen. They can accept hydrogen bonds from neighbors, but they don't have any hydrogens. Okay, so they're a little bit stronger in terms of intermolecular interactions than just an alkane, but much weaker than an alcohol. Okay. Yeah, so we'll see alcohols with similar masses have higher boiling points than ethers, and alkanes are way lower. All right, so let's just look at a chart here. So first of all, just like we saw with alkanes, let's focus our attention right here for a second. Notice that these are all alcohols and they're increasing in their number of carbons. So just like we saw with alkanes, you increase in boiling point as the chain grows. Okay, so the smaller the alcohol is, the lower the boiling point's going to be compared to a much larger sized alcohol. This same trend you'll observe, again, we saw it with alkanes, we see it with alcohols, we also see it with ethers. So here are our ethers, and notice that as I'm increasing in the number of carbons, my boiling point is also increasing. So in general, the larger the molecule is, the higher the boiling point is, if they all have the same functional groups. But now let's take a look at the big difference that these different functional groups make. I mean, first of all, let's just compare methane, a 1-carbon alkane, with methanol. Look at what the difference that OH group makes. We go from having a boiling point of negative 161, so that's super duper cold before you can get it into the liquid phase, to now a boiling point of 65, right? So you're talking about more than 200 degrees Celsius difference in the boiling point of these two compounds, all because of that OH group. All right, that's a significant jump just by putting on that OH group. And again, that's because alcohols can hydrogen bond. Okay, now let's take a look at similarly sized, let's take a look at ethane. So this has 2 carbons. Ethanol also has 2 carbons, but it has an OH group. And then dimethyl ether also has 2 carbons, but now is an ether group instead of an alcohol group. Okay, ethane is our lowest, sort of ranked the lowest there. When we go to dimethyl ether, we go a little bit higher. So you can see the effect that that high oxygen has on the boiling point. We get a little bit higher. But then we see another huge jump with, instead of being locked in the middle of two carbons, when it's an OH group. Okay, so you can sort of look over, compare again, like a 5-carbon alcohol to a 5-carbon ether. You can sort of convince yourself of this using all these examples. But the bottom line is an alcohol group, that OH group is capable of really strong intermolecular interactions called hydrogen bonding. Ethers are a little bit of, they can do a little bit of hydrogen bonding, but not much. Okay, now let's talk about solubilities of alcohols. Okay, small alcohols are soluble in water. Large alcohols are insoluble in water. That's because every alcohol has kind of like this push-pull aspect to it. This back end, the hydrocarbon chain portion, is nonpolar. But the OH group, that hydroxyl group, is very polar. And so there's kind of got these two halves, right? Part of the molecule is nonpolar, part of the molecule is polar. And so depending on how long that carbon chain is, if it gets long enough, it'll end up winning, so to speak, and the molecule will not be soluble in water. If it's short enough, then it will be soluble in water. And actually, there's sort of these rules that we use. If it's less than 4 carbons, so methanol, ethanol, propanol, those are 100% soluble in water. If it has 4 carbons, so butanol, we call butanol slightly soluble. What that means is if you had a little bit of butanol, it would dissolve in water. If you tried to put a bunch of butanol in, it would not. And then if we have more than 4 carbons, these are insoluble in water, right? And again, that's just because, like, so for example, what do we have? 2, 4, 6, 8. In this case, octanol, that non-polar end of the molecule is just too large. Okay, it won't let it dissolve in aqueous solution. Phenols. So phenols have, if you count, 6 carbons. We would think that that would be insoluble, but actually phenols are slightly soluble in water. Okay, they also kind of have that same sort of push-pull where this portion here is non-polar, but this portion here is polar. Okay. However, phenols have another sort of odd property that makes them very different than alcohols, and that is that the hydroxyl group on a phenol can act as an acid and donate that proton. Alcohols, ethanol, methanol, etc., they don't act as acids ever. Well, not ever, but you need a really strong base to be able to remove those protons. Phenols, you don't. Okay, so that can, and it's kind of complicated and we're not going to go too far into it, but the bottom line is that the negative charge that you get by removing that alcohol or that hydrogen is sort of spread throughout that ring, making it more stable. And because of this, because it can ionize slightly, that's part of, or that's what makes it slightly soluble instead of insoluble. All right, ethers, they can form hydrogen bonds with water. I'm going to say kinda. Again, they can form a bond one way. They can sort of let their oxygen talk to water's hydrogen, but they don't have their own hydrogen to donate as well. Okay? Way fewer hydrogen bonds than an alcohol has with water. So ethers, even the small ones, are only slightly soluble in water. So we say if they have fewer than 4 carbons, they're slightly soluble. Anything more is insoluble in water. Okay, so now let's see which ones, which of these is going to be soluble in water. We have a really small alcohol and a really long alcohol. Which one do we think is going to be soluble? Again, the rule is less than 4 carbons is soluble. So this is 1, 2. This would be ethanol, and that would be soluble. 1, 2, 3, 4, 5, 6. This would be 1 hexanol, just to sort of practice our nomenclature here. That's too many carbons, right? So now that's more than 4, so this would be insoluble. Okay?